right, so for today's lesson, we're going to look at different types of changes that can occur to equilibrium systems. So we're looking at qualitative changes today. Okay, so this is looking at different things that can impact a system, not necessarily from the point of view of calculating the concentration change, but more so just talking about the change in the rate of reactions. So meaning perhaps the forward reaction will increase in the rate or the reverse reaction, and different ways that equilibriums can change. So the main principle we're going to talk about today is called Le Chatelier's principle. Okay, so this is essentially looking at what happens when equilibrium systems have stressors that are applied to them. So meaning naturally in a closed system, right, equilibrium will reach after a certain amount of time. However, there are things that can be done, and sometimes you may even want to do them, that can cause the equilibrium to change or to shift. You're going to hear me talk a lot about shifts. So in order to adjust the equilibrium, what happens is it tries to alleviate whatever stress has been applied. So we're going to talk about, well, when we say the term stress, what exactly does that mean? And we'll also look at, well, what does the equilibrium system do under such stresses? So in terms of stress, we're not talking necessarily about, the mental health of our equilibrium. More so looking at any factor that will upset the balance of the rates. So remember, equilibrium means that the forward and reverse reaction rates are the same. So basically, anything that will cause the rate of one or the other to change is considered to be a stress. Okay, so there are a bunch of stresses that we're going to talk about. So we have concentration change, pressure or volume change, temperature change, adding a catalyst, or adding an inert gas. So when we talk about inert gas, we're talking about the noble gases, right? So for example, adding neon or argon. Now, I will say the first three are legitimate stresses. The last two are actually not really true stresses in the case where it's going to affect the equilibrium itself. But they're more sort of just changes that could exist, and you'll see what I mean when we get to them. The first three are factors that can be adjusted to actually change the rate. All right, so we're going to look at one at a time here. So we have concentration first. So concentration, how I want you to think of this, and I'm going to use this example a lot. Okay, so imagine we have all AQ. Okay, so whatever change is made to an equilibrium, okay, the system wants to maintain equilibrium. So by us causing a change to the rate, it actually wants to combat that change. Okay, so I'll give you an example. Let's say we have this in equilibrium, and all of a sudden we're going to add in more B. Okay, so the equilibrium is happening nicely. The rate of the forward is equal to the rate of the reverse reaction. And we're going to open up our container and we're going to dump in a bunch of B. Well, what ends up happening is the equilibrium wants to try and get rid of whatever was just added in. Okay, so if you're adding in B, it wants to basically get rid of that extra B that is in this equilibrium. Okay, so the only way for it to do that is to transform the B by doing the forward reaction, right? So the B can react with A and cause more C to be produced. So what happens is by adding in B, we've caused an increase to the forward reaction. Now, does that mean that the reverse reaction is not happening? No, the reverse reaction is still happening. But what's happening is the reverse is slower in comparison to the forward. So what ends up happening is we call this a shift. Okay, so we say that we've caused an increase to the reactant's concentration. So as a result, the rate of the forward reaction will increase. So sometimes we can call this a shift to the right-hand side, or a shift to the product side, or we're making a shift to make more product. Okay, so that's actually this third point here. So increasing the concentration of a reactant causes a shift to product formation because it wants to use up that excess reactant that was just dumped in. The same thing would happen here if we were to add in A. Okay, now let's say instead of adding in a reactant, we were to add in a product. Right? So let's say we were to open this up and we're going to increase the concentration of C. So what ends up happening is the equilibrium wants to use up that extra C that has just been added in. The only way to do that is to convert it by using the reverse reaction back into A and B. So what ends up happening here is we're creating a shift to the left, or we can say that it is a shift to the reactant formation or to the reactant side of this reaction. So by adding in product, you're going to use up that product to make more reactant. So remember, this does not mean the forward reaction is not happening. It just simply means that the rate of the reverse is now much quicker than the rate of the forward. It's causing the rates to no longer be the same. So afterwards, we're probably, well, can we just simply add in stuff? Well, no. What if we were to remove some components, right? So let's say I were to remove some A. Okay, so I'm going to have A decrease in concentration. Remember that the equilibrium wants to get rid of whatever change has just been made. So if we take away A, what will happen is it will want to try and replenish what has been removed. So what happens here is if the concentration of A goes down, C will actually be producing more A and B to try and bring that concentration of A back up once again. So we have a shift to the left. The exact same thing would happen if we were to decrease the concentration of B. Right? And as you can imagine, if we were to remove C instead of removing A, we would have the opposite. If we remove a product, it's going to want to shift to the right to produce more product because it wants to replenish what has been lost. Or we can say we have a shift to the product formation. So you're probably wondering, well, like what happens after all these shifts have happened? Okay, so eventually what would happen is the rate, like let's say we replenish this C concentration, it will eventually get to the point where the rate will begin to slow down and the reverse reaction will then be equal to the forward reaction once again. So anytime there is a shift in equilibrium, there will be a reaction to that shift, right? So there'll be some sort of stress applied, a reaction to that stress by having it go either increasing the rate of the forward or of the reverse. And then what happens is a new equilibrium is established after that. So it's best to see it maybe, let's look at this graph here now. I'll go back to that last slide. So here we have a very simple reaction. So we have one reactant and one product. So we have the red line representing a product and the green line representing the reactant. Okay, so you can notice here, this was in equilibrium already, right? So when we talk about a stress, the stress is always implemented when it is already in equilibrium. So we have equilibrium. All of a sudden, if you notice, there's a big jump up with the concentration of a reactant. So more N2O4 has been added. So this has been added in. So what ends up happening as a result is the equilibrium will shift to try and use up that added in N2O4 to make more product. So if you notice, if you look at the product concentration, it was in equilibrium, and then all of a sudden it increased. The reactant, even though we added a bunch in, you can notice that the reactant starts to get used up again. So the concentration is beginning to decrease. However, after a certain amount of time, you'll notice that a new equilibrium is established. So at this point in time where I have the star, this is where the rates are no longer equal. The forward reaction rate is happening much quicker than the reverse reaction rate, right? So we are making product. So at the point here where we now have equilibrium once again, notice the concentrations will never be the same as to what it was at the beginning, because it just simply, it can't be. You have more atoms there. So you can't decrease in concentration. The atoms can't, if you've added in more molecules and more atoms, they're not all of a sudden going to disappear. They have to be accounted for. However, by causing some of them to move forward into the product formation, you end up having a new equilibrium being established. So in equilibrium, we applied a stress. So in this case, the stress was adding in reactant. There was a reaction to that. In this case, it was a shift to the right. And then a new equilibrium was established. So the process is always the same. Equilibrium, a stress, a reaction to that stress, or a shift occurs, and then a new equilibrium eventually is established. So let's go back for a second. So in this case, we have a reaction, and it's in equilibrium. So we have hydrogen is being added to the mixture. So imagine this is an equilibrium. We're all of a sudden going to add in more hydrogen molecules. So what ends up happening is to try and alleviate that excess hydrogen, it's going to do the only thing it can do, which is turn that hydrogen into hydrogen iodide, of course, reacting with iodine in order to do that. So what ends up happening is you have more product, and then the reactant rate, so the forward rate increases, the reverse rate decreases, and then eventually you would have a new equilibrium. So the shift that happened to try and alleviate that stress is a shift to the right. So you can see that in a bunch of different ways. We can say it shifts to the right, it shifts to the product side, the forward reaction is sped up. You can say this in a bunch of different ways. It means the same thing. You're making product because you've added in excess reactant.